Welcome back.
To school.
Yeah.
For the first section of the year, section 1.1, we're going to model. We're going to do modeling and equation solving.
Now, modeling is not like, walking the catwalk in New York City. It's a little different.
Oh, I thought you were going to talk about like a clay model.
Well, it's not that either, what Miss Parham does.
Although I would say that in some ways it is similar to a clay model.
Okay.
Because you are representing something with something else.
And you got to use your hands to mold it correctly.
Yeah.
Okay. All right, let's dive in.
In math, there's typically three ways that we model data.
Okay.
Numerically.
Yep, I like that.
Which means using tables.
Right.
Algebraically, which means using equations.
Okay.
And graphically, which means using graphs.
I like it.
So, we're going to have an example here that it's quite an example. It's pretty lengthy, and it all has to do with this data that is about the minimum hourly wage over the years. That's this first column.
So people in 1955 earned 75 cents an hour.
If they were on minimum wage, that's correct. Now, what's interesting is that they've also figured out somehow the purchasing power of what the dollar was then compared to what it would have been in 1996.
Oh,
because 75 cents in 1955 is not like 75 cents now. Like, you can't even buy a Coke hardly for 75 cents
Back then,
now.
you could get a Coke for like a nickel or something.
Yeah, exactly. So that's what this other column is for, is it's showing on kind of a more standardized line of, in 1996, this is what that amount would have been worth.
In a dollar amount that we would be more familiar with.
Right.
Yeah. Okay.
So in this example, we are going to answer some questions. So part A, in what 5-year period did the actual minimum hourly wage increase the most? MHW stands for minimum hourly wage. So when did it increase the most? Well, that requires us to look at between each of these and figure out which one of these has the biggest gap. So like these are, I can actually eyeball.
That's 25 cents.
25, 25, 35.
35, yep.
50. But here's a dollar.
A buck. A whole buck.
So, and then, and you might make notes on this to help you keep track. That looks pretty good right there, that dollar increase. 25
cents. What is that, 45 cents maybe?
Yeah, 45.
45 again.
45 again. Now, this is 90 cents.
Oh, that's close.
That's close, but, and then this is 0.
Oh, it didn't change.
So, from 1975 to 1980 would be the period where it increased the most. And so we just had to check how much did it increase each time and then pick the biggest one.
You're finding the difference. So difference is subtraction, right?
Right.
Okay. And
what year did a worker earning the minimum hourly wage enjoyed the greatest purchasing power?
So in other words, when we're looking in those $1996, I want the most bang for my buck.
Right.
Right.
So even though this column continues to go up and up and up, this one actually goes up and then comes back down.
Yeah, fluctuates.
Kind of fluctuates down here. So 647 is the biggest number in this column. So in 1970,
biggest one that I see.
That's whenever you had the most purchasing power.
Right. Okay.
So back in the day. Okay, part C. A worker on a minimum wage in 1980 was earning nearly twice as much as a worker on a minimum wage in 1970, and yet there was great pressure to raise the minimum wage again. Why would this be?
Well, I would think that the purchasing power would have the biggest impact on that. It's like the minimum wage discussions that are going on today.
Yes.
So you want what you have to go as far as possible.
Right. If you look at 1970, you're at $1.60. In 1980, it's at $3.10. But how much it's actually worth is $6.47 versus $5.90. That's about a 50-cent difference. So I would say inflation had to do with that.
Yeah, or something like that, yeah.
So how do we want to say that?
So, why was there pressure? Because in 1980, the $3.10 would not buy as much as the 1970 $1.60.
That's really well put. I wonder if I can remember all that. In 1980, the $3.10
would not purchase
as much
as the 1970 $1.60. Now, you can reword this a little bit as well, but this is going to take a complete thought to actually answer this question. It can't be because 1980 happened.
Yeah, or because more.
Right.
You know, like, that doesn't make any sense. Like, whenever you see the word why, a lot of times you need a complete sentence.
Right.
Because typically complete sentences mean complete thoughts.
Correct.
Kind of, in general.
All right.
So now we'll have to go to the next set of subpoints here. You'll still be able to see all this because you've written it down, but we're going to go right here. We're going to model the data graphically with two scatter plots on the same graph so that you can see.
I'll just type these in real quick.
We're going to do it two ways. We're going to do it on our paper. You have a graph provided there. We're also going to show you, and a calculator should pop up here on the side. We're going to show you how to make a scatter plot in your calculator as well. So if you need to rewatch this section more than once,
building a scatter plot is pretty handy on your calculator. It helps in more ways than you even know right now, but it's a good skill.
Right. Now, one thing that we do a lot of times with scatter plots when we have years is, notice here it says measure time in years since 1955. So that means that instead of starting out with 1955 here at the bottom on my time scale, I'm actually going to start with 0. And then my years are going up by 5s. What am I going to...
Stop at 50.
Stop at 50. And then we have a range of numbers as far as our dollar amounts that we have to pretty much be almost from 0 up to about $7. So I think I made this graph to where you could go up by 50 cents on each mark. So
just need to go
here would be
which one are we doing? Purchasing power?
We're going to end up doing both.
Okay, so you need to go, up to about $7.
Okay, so each line is 50 cents, so I just labeled every other line. And then you would go through and you'd preferably have like 2 different colors or maybe a pen and a pencil, and then you'd be able to mark out points for minimum hourly wage. When you're on your calculator and you're doing this, there's a way to set it up to where there's 2 different kinds of marks going on.
Right.
So on 1955, we're at, which is at 0 years, we're at 0.75. So that's right there. And then 5 years later, we're at $1. And then we're at $1.25. Then we're at $1.60.
$2.10. $3.10. High cotton. $3.35. $3.80.
Oh no, hang on. $3.35.
$3.35. $3.80. $4.25. And $5.15 twice.
And our book is kind of old, so we actually know that in 2010, I don't know when it actually went up, but right now isn't it higher than $5.15?
I believe so, and I believe they're talking about maybe raising it again.
Yeah, they've talked about it again for that same reason we mentioned of the purchasing power. All right, so that's one color. And you can see that this looks pretty linear.
Yep, pretty straight.
And we could say that there's a correlation because of how straight that is, and it's a positive correlation.
And it's a pretty strong correlation because all the data is pretty close together.
Right. All right, so on the other one, 439, and then 530.
623. 647. 612, 590, 488, 456, 438, 469, and 415.
So this is much less linear.
Much
not
less
really-
correlated.
yeah.
It's more loose.
And so, whereas with the first set of data, because we've looked at it like this, we can see there's definitely a connection in the years gone by and the minimum wage. You cannot say the same thing about years gone by and how much that money
Right, because
is
we
worth.
actually started off.
Pretty good.
Well, we're now
Well,
earning less than we started in 1955.
Yeah,
So
that's true.
right.
So we're on part E. We're going to model the data algebraically with linear equations of the form y equals mx plus b. You write one equation for each set of data. Use the 1955 and 2000 ordered pairs to compute the slopes. Are these equations good models of the data? So in 1955, for our minimum hourly wage, I guess I should have switched back to blue for that. Our minimum hourly wage, if we use the 1955 data point, that's 0,0.75. And then the 2000 one would be, that's 45 years after we started when we are making 515. Now, why would we pick these two data points? Because if we look on our graph, that's this point and this point, and if we drew a line between there, that'd be a decent
It's pretty
line.
straight.
So,
I accidentally.
did you find it?
I did a regression on the whole thing.
And that's good. We'll see how close that is.
Okay, sounds like a good plan.
But before we do that, in order to get a line from this, we need to use point slope form,
Right.
and we need to use that slope equation.
Yeah, the one, stop
Yeah.
minus start sort of thing.
Yeah, m equals y2 minus y1 over x2 minus x1.
Right.
So 515 minus 75 cents
It's going to be 440,
over 45.
which is 0.0977 repeating.
Okay, so that's
your slope.
0.098.
Yep.
And the great thing, though, about this, if we use this point and point slope, which is y minus y1 equals slope times x minus x1. Since x1 is 0, all we really have to do is just add that
slide
over.
that guy over. So we would need 0.098 times 0.75.
No, we don't.
Well, if you...
We just have
No,
to...
you don't. No, you don't. I was just kidding.
You were just kidding.
I was
That
just
was
checking.
a good joke.
I
So
was
this
just-
is our line of best fit we came up with. You can use your calculator, though.
And let me get back to it.
And so it all has to do with, we showed you, as this video went along, we showed you how to put these data points in your calculator, and then you type in, or you go to the menu and do linear regression.
Right.
And it gave us
0.968, which is 0.97, which is really close.
pretty close.
But the y-intercept was different. It was 0.443 instead of 0.75. So it's a pretty close.
Yeah.
It just happens to work that way on this collection of data. It doesn't necessarily always work that well when you take that first point and an end point.
Right. And now if we do the same thing with our green data here, which is the purchasing power, and we use the first data point, which is
0.439.
and the
2000 would be 469. I don't feel like that's going to be a very good representation.
I don't feel like it is either. Our slope, we do 469 minus 439 over 45 minus 0.
So it's 0.3 divided by 45, and that is 0.006 repeating.
0.006 repeating. Okay. And then if we want to be smart, we can already know actually that this is the y-intercept.
Yeah, do that guy.
Y equals
And I'll do a complete regression here.
0.0067x plus 4.39.
Wow. It doesn't match at all.
It doesn't match at all.
Not even close.
But either way, it wouldn't have been a very good representation. No. This is the line that we just found. Like, does that at all represent this data well?
No.
No, not at all.
And the linear regression, which I would argue that that's not even the best way to look at this data.
No, probably a different kind of function.
Yeah, I would say so. This linear regression gives us the equation y equals negative 0.026x plus 5.84.
Wow, so that's
so
very
they had
different.
A negative slope and everything. So it's not the same.
So the in question, are these equations good models of the data? I would say that the first one is.
Yes, the blue equation, definitely a very good representation.
But the
green one is it's terrible.
And so last, if the minimum wage continues to follow the linear model found in E, what will the minimum wage be in the year 2015? Now, this is just around the corner from us. Actually, it's 2014.
We can see if it's going to line up.
And so we would take this model right here.
Yeah, we'll use that one and not the one I found on my calculator.
And we're just going to put, how many years is it from 1955 to 2015?
That's 60,
That's
right?
60 years. So that's what goes in for X. You would not want to put 2015 in for that.
No, don't do that.
And you just figure out what this is.
$5.96.
$5.96.
Which I think minimum wage is actually $7 or something like that.
I thought it was, I don't know.
I don't either.
We don't make minimum wage.
We don't. We make less than that, so.
Well, that's a whole other story.
So,
let's not get into that.
All right.
But the whole point is that because we had data that followed kind of a linear fashion, that allows us to try to predict what might happen in the future.
Make a good prediction.
Yes, and
not
that's
some crazy
one of the
prediction.
Cool things about mathematical modeling.
Indeed. All right. A couple more examples, a lot less involved than that behemoth of number one.
Right. So that first example, that's like a huge chunk of a problem. But we're also in this section going to do some simpler things, like solving equations algebraically and graphically.
Simpler.
In some respects.
In some respects, like that, I don't look at that and go, "That's a simple solve."
Right. So we are past the point of two-step equations. Like you should be able to solve a two-step equation without having to really review that.
We're putting on our big boy and big girl pants today.
Yes. So if you're solving algebraically, you just need to think of that as not graphically. That's basically what that means. Like you can either do it algebraically, which is by hand, or you can do it graphically, which means put it in your calculator.
Right.
Let the calculator
show all the steps on algebraic.
Yeah.
Like you can't write down x equals 5 and then we go, hey, good job, because there was no algebra at all shown.
Even if you can somehow guess and realize that, like that's not the point. The point is to actually be able to follow the steps and the rules.
So you got to have those rules. They're pretty important.
Yeah. So we're gonna end up having to factor, use the quadratic formula, stuff like that.
Okay, let's do it. Well, first let's get all the x's on one side.
Yeah, in this example, let's get all the x's on one side, and since the highest power is this x cubed, I think everything should move to the
I agree.
left.
Let's leave the x cubed positive. Just makes life simple.
Now, when I move this over, remember that you are subtracting 11x squared from both sides in order to move it, and you are subtracting 10x from both sides in order to get those to move to the other side.
Right.
And that's how we get a 0 on the right. Once we have a 0 on the right, then we can try to factor.
Yeah, and also, even though we're not doing it at this point, once you have that 0 on the right, you can graph it as well.
Right.
So that's also important.
Because you could always check it.
That is correct.
When I look at this and I try to factor, I'd say, looks to me like they all have an x, so I can take an x out.
I would concur with that assessment of the situation.
Which makes these all have 1x less than it did before.
Oh, looky there. A quadratic. Now, we have lots of tips and tricks and tools to use to solve a quadratic, one of those being the quadratic formula every single time.
Yes. You can always use the quadratic formula, but sometimes factoring is easier.
Right.
Or depending on your algebra 2 teacher, you might try slide and divide or using some kind of boxes.
Right. So it just depends on what your personal factoring mode of.
Well, what do you think we should do here?
Whatever you want. You're driving, so
okay.
you pick the way, and we'll go with that.
I like slide and divide. So slide and divide, you take this number in front and multiply it to the last number. And then from this point on, we're kind of going off of the equation path. We're kind of doing some side notes here. So we're not going to put equals 0. Because
no algebra rules violated, by the way.
As long as we don't put equal signs at this point.
Right.
Nothing we're doing, this is like side note work, okay? Now we're going to factor this. So what multiplies together to get negative 60?
Well, you got 5, you got 6 and 10. You got 5 and 12. You've got 20 and 3 and 30 and 2.
Yeah, I don't think this is factorable.
You got...
Because I was thinking a positive 60. If it was positive 60, we'd be good, because then we could use... No, I don't know what I was thinking. Summer has been too long.
All right.
Do you see a way?
Not off the top of my head, so I guess that means quadratic formula.
Let's quadratic formula it. So let's get rid of this.
And you know, if quadratic formula pops us out an even number, then we'll know that we
we'll
had
know
a little
that we
mistake
done
in there somewhere. So A in this case is going to be 6. B will be negative 11, and C will be negative 10.
And I think we all know the quadratic formula song, don't we?
Yeah, we're not going to sing it.
Okay.
You can sing it.
X
I'm not feeling real singy.
Negative B plus or minus square root.
B squared. That's a negative 11 squared, by the way.
Make sure you put it in parentheses.
In parentheses. Like if you punch it into your calculator, negative 11 squared, you get negative 121. That's not correct. But if you punch it into your calculator, parenthesis, negative 11 parentheses squared, you get positive 121, which is totally different.
Right. You want to start pushing some buttons on your calculator?
I'll button push. So while you're writing that down and explaining the process.
The other thing that you'll see us say a lot in this class is to give us an exact answer. An exact answer is not a decimal. An exact answer would be something like 11 plus or minus the square root of
361
over 12. Now does 361, does that
I don't know that
you
that's
can't
square
divide
roots.
it by 3.
19.
Ooh, look at that. What are the odds?
I don't know. 11 plus or minus 19 divided by 12.
So that gives us 30 over 12. And 11 minus 19 is negative 8 over 12.
Now, for us, believe it or not, those are good answers.
Technically, yeah.
We don't, we're not going to make you reduce. However, most of you have been pounded into your brains. Oh my gosh, I can't believe it is 30 over 12. So do not write a mixed number ever.
Yeah.
Ever.
Improper fractions.
But an improper fraction is beautiful.
So 30 over 12, both are divided by 6 to get 5/12. 8 over 12 is
4/3. 2/3.
2/3. Negative 2/3. And that, I think, is the problem. So we may have been able to slide and divide there. We probably could have.
Probably.
But
you could have boxed, slide and divide,
or use the
or
box
whatever.
on that.
Or you could have guessed and checked your way through.
Yes.
So we could have factored that one, as it turns out, but that's okay.
Now, what about this x in front?
Well, he still is there,
so,
but he is set equal to 0.
Yeah. The thing is that at this point, really, what we did is we took 6x squared minus 11x minus 10, and we said that equal to 0 is solved using the quadratic formula. But we also have to do that with the x in front, so x equals 0 is also an answer.
Yeah, and we're going to talk about this a lot more, but the degree on this problem is a third power.
Which means you should have 3 answers.
You should have 3 answers, and we do.
Conveniently enough.
Convenient.
Let's just jump right into example 3.
Okay, I already don't like example 3 because it has a square root, like, set apart from other stuff.
Right. So my suggestion is that we get the square root by itself.
Positively by itself?
Preferably.
Yes.
I mean, it's pretty easy to do that. We can just add this square root.
And, what are you adding to both sides? The square root of 49 minus 4x.
Yes.
Like the whole thing.
That whole thing. None of it gets left behind or forgotten.
Right.
So x minus 1 equals positive square root of 49 minus 4x.
Whew. Now, here's a real tricky situation. We're going to have to eliminate that square root.
Right. How do you get rid of a square root?
You square everything.
Okay.
Now, we're also now introducing the opportunity for a number to maybe not work.
Yes.
So
because the degree of this is really 1.
yeah,
We should get one answer. But now that we're squaring things, we could end up with 2, so we're going to have to check our answers.
we
and
will
make
have
sure
to
they're
check
right.
our answers.
The other thing that you may make a mistake on is x minus 1 squared means to do x minus 1 times
If you
x
write
minus
down
1.
x squared plus 1 or x squared minus 1
That's wrong.
for your answer, I might kill a kitty.
That's terrible to say. He wouldn't
You know,
really do that.
I would do that
No, you
because you know
wouldn't.
what's terrible? Students who take x minus 1 squared and do x squared plus
It's
1.
like the first day of school. It's
No,
really not that
maybe
big a
a
deal.
puppy even.
Let's
Maybe
foil.
one of each.
Let's-
So don't do it.
Let's foil and let's move on. Foil first. X times x is x squared. Outer x
Minus
times negative 1.
2x
Right, and then this
plus 1. The quick way to do that is to square the first and last terms.
one.
And then
add
2 times the first term times the second term.
Right.
And then boom shakalaka.
So now we want to get everything on the
Yep,
same
everything
side.
on the same side. And since we're dealing with x squared, we want to move it all over there to that side. So we're just going to hop those two right over.
It's a nice British accent.
Every now and then I get a nice accent. Doesn't happen too often, as you're aware. Starts off
X
one and
squared
goes somewhere
plus
else.
2x minus 48.
Oof. 6 and 8.
Hooray! So whatever multiplies to get negative 48 and adds to get 2 are the numbers we use. And
So plus 8 minus 6.
I feel like you got better at factoring over the
You
summer.
know, I maybe went to a math conference or something.
2 or something. So we said each part equal to 0 to solve. That should be easy for you to do in your head. X plus 8 equals 0 means x equals negative 8, right?
Yep. And now
And-
look, we're going to get 2 answers here. So one of these probably is not going to work. What's the easiest way to do to check on that?
Plug them in, plug them in.
Plug them in, plug them in.
I would say that I don't know which one's not going to work. So, like, we actually literally, and this is where you can use your calculator to help you, like,
Right.
negative 8 minus 1 minus 49 minus 4 times negative 8. We're looking to see if this really equals 0.
Yeah, if that doesn't really equal 0, it's no deal. So
This is plus 32. 49 plus 32
49 plus 32.
is 81.
81.
The square root of 81 is 9. 9, that's close.
It's close, but,
But no.
negative 9 minus 9, that's negative 18.
Right. Let's see if
And-
the other one works.
Hopefully the other one will, or we could be in deep duty.
Well, otherwise we messed up
Yeah.
somewhere.
And somebody over here is doing all the working right now.
So this is 5 minus, and this would be 49 minus 24, which is 25.
25.
Which is 5, which
Hey.
means that's the right one.
There we go. So we'll take that guy, not that guy.
So x equals 6.
Boom, shakalaka.
Graphically,
Oh, I love graphically.
so there's 2 ways of going about graphically.
Both are correct.
Right, but the book does specify the way it wants you to do it.
Right. However, we are freewheeling thinkers. So as long as you are algebraically correct.
Right, as long, well, yeah. Okay.
Yeah.
Okay, so they tell you in the book to get everything on one side and then put it into y1 and find the x-intercepts. And
Right.
that's a great way of doing it, and in a lot of ways that can actually be easier. The
Yes.
other way of doing it is to put the left side in as y1, the right side in as y2, and then find where they intersect.
Right.
Sometimes finding where they intersect
That can be really
is
difficult.
rough. Whereas if you get everything on one side and you're looking for where it goes to the x-axis, you at least know, hey, it should be somewhere on the
Right,
x-axis.
right. So those are your drawbacks. And sometimes if you have a really wacky y value potentially or an x value, if you're trying to find the y1 equaling y2 part, it can be really hard.
Yeah. So just get everything on one side, and so it's quicker to move the square root over and do 0 equals 6 minus 2, absolute value 5 minus x, and then minus the square root of x plus 6, which we moved. Now this is a good opportunity for us to tell you that the absolute value button is in the math menu if you're on a TI 83 or 84, It's math and then number.
Math num, and then abs.
And it's the very first one, ABS. And
If
on
you're
the
on a-
older ones, it gives you abs with parentheses.
Right.
Newer calculators puts the bars for
Right,
you.
in the Inspire, you can just type in ABS. So 6 minus absolute value 5 minus
Did you
X
put 2?
minus.
Did you put
Yes,
that too?
yep, I
Okay.
got the 2. All right, we're good to go. So we're going to graph that sucker.
Now, when you graph, especially if you did some scatter plotting earlier, you would want to zoom standard.
Now, that's not always the best window to look
But
at.
it's a good start.
But it's a good start.
Zoom
like
6.
it gets you neighborhood-ish of the origin with a good view.
Yeah.
Yep.
Now, we should have a calculator up
Yes, we do.
while
Yeah.
we're doing this. So you should see that we've got like a downward V.
Right.
And now the steps on figuring out where those x-intercepts are is to use the calculate menu. You
Right.
do,
So that's going to be second trace.
yeah, second trace on your old
And
calculators.
if you're looking for where you cross the x-axis, that's actually called a 0.
Right.
Or if you have a really old calculator, it's called a root.
Ooh,
Yeah.
that's old.
Yeah, that's...
Now, whenever you do this on either calculator, it's going to ask you for either 2 or 3 things. It's going to ask you for a left bound, so you want to move to the left of a 0.
Or a lower bound, depending on your calculator.
Right? And so you want to go to one side of your 0, and then it's going to ask you for the other side, so you have to move the cursor to the other side of the 0. And then on 83s and 84s, it asks you to guess. Well,
I don't know why it asks you to guess. I think it's an awkward in-between step.
Yeah, so you can just press enter when it says guess, or you can move it closer to the 0.
But anyway, the 0 closest to the origin
is 3.545. Notice I used 3 decimal places.
Yep, those AP graders really like to see 3 decimal places.
So that's how we're going to practice 3 decimal
That's right.
places. You are allowed to round or truncate.
Yep.
Truncate is a fancy word for cutting off. So I could have put
4-4.
Yeah, I could have put 4-4, and that would also be correct. So same process, but now we're going to go left and right on the other 0.
And get to the right-handed side, and after the guessing is 6 1/4.
Ooh, no rounding
6
required.
1/4. It's your minimum wage back in 1972.
No, it's not.
Oh, well, what was it? Wasn't it 625 somewhere?
That might have been
That's
the purchasing power.
Okay.
It's okay.
All right. Have fun.